Welcome back. Let's practice using the dot product. Alright, so here's our first example. We have two vectors, vector v and vector u, and for those two vectors, we want to find the following. We want to find the dot product of vector v and vector u, we want to find the dot product of vector v with itself, and then we want to find the magnitude of vector v squared. And I know that that one seems a little bit out of place at first, but you'll see why this is here in a little bit. But first, let's work on our two dot products. All right, and so for these two dot products, notice that vector v and vector u are both two-dimensional vectors, right? Both of them only have two components, an x component and a y component. And so when you want to perform the dot product for vectors in two dimensions, here's the formula that you use. The dot product of vector v and vector u is equal to v1 times u1 plus v2 times u2. It's the sum of the products of corresponding components, right? So v1 represents the x component of vector v, u1 represents the x component of vector u. We multiply those x components and then add that to v2, which is the y component of vector v, multiplied by u2, which is the y component of vector u. All right, so all we're doing here is multiplying the x components and adding that to multiplying the y components. And so let's find this first dot product here. Notice that vector v and vector u are in two different notations. It's not a big deal, we can work with them in these notations, but if you prefer to have them both in the same notation, then it might be a good idea to rewrite one of them. All right, so vector v is in this standard vector notation, and then vector u is in the standard unit vector notation, where we have I and j. I'm just going to rewrite vector u to be in the standard vector notation, where the components are 7 and 5, right? The x component is 7, and the y component is 5. And so now, for this dot product, we'll have the x components multiplied together. So we'll have negative 4 times 7, and then we're going to add that to the y components multiplied together. So we have 8 times 5. So I'll write that down. 8 times 5. And now let's simplify. Negative 4 times 7 is negative 28. So we have negative 28 plus 8 times 5, which is 40. So we'll have 40. All right, now negative 28 plus 40 is going to be 12. And so our final answer is 12. That is the result of performing the dot product between vector v and vector u. And notice that that result is a scalar value. It's not a vector, and so when you use the dot product for two vectors, you're not going to get a vector, you will get just a scalar value. Just a single number with no associated direction or anything like that. It's not a vector, it's just 12. All right, now let's move on to our next dot product here. This time we have vector v multiplied by itself via the dot product. By the way, that's what this dot means. When you see a dot between two vectors, that means that you want to find the dot product of those two vectors, in case that wasn't clear before. And so if we're going to multiply vector v by itself, we're going to be multiplying the x component by itself, and then we're going to add that to multiplying the y component by itself. So we'll have negative 4 times negative 4 plus 8 times 8. Okay, now if we simplify, negative 4 times negative 4 is positive 16. So we'll have 16 plus 8 times 8, which is 64. So we have 16 plus 64, which is equal to 80. And so 80 is a result of the dot product between vector v and itself. All right, and so now let's take a look at this last operation here. We just want to find the magnitude of vector v squared. And so let's do that. Remember that the magnitude of a vector is equal to the square root of the sum of the components squared. So we'll have negative 4 squared plus 8 squared. But we're squaring that magnitude, so we need to square that square root. Now the square and the square root will cancel each other out, so this is just going to be equal to negative 4 squared plus 8 squared. So we'll have 16 plus 64. And notice that that's the same thing that we had up here, right? 16 plus 64 is equal to 80. And that's not a coincidence, right? It's actually pretty significant that these two values are the same. This is actually one of the properties of the dot product. The dot product of a vector with itself is going to be the same as taking the magnitude of that vector and squaring it. This is true for any vector, whether it's in 2D or 3D. You can just take the magnitude of the vector and square it, and that's the same as performing the dot product of that vector with itself. All right, so that's something to keep in mind going forward. But now let's take a look at 3 more operations involving these two vectors. First up, we want to find the dot product of vector u and vector v, and then multiply that by vector u. So let's do this. And note that if we took the dot product of vector u and vector v, that's actually the same as if we took the dot product of vector v and vector u, right? Vector u times vector v is equal to vector v times vector u. One of the properties of the dot product is that it is commutative. It doesn't matter what order the vectors are in when you find a dot product. And so remember from the previous set of operations that we already found the dot product of vector v and vector u. We found that it was equal to 12. So we can use that result here. We can save ourselves some time and not do this dot product again, and just use our knowledge of the properties of the dot product to say that, well, since the dot product of vector v and vector u is 12, then we know that the dot product of vector u and vector v will also be 12. It's the same thing. So this will be equal to 12 times vector u. And so all we're left with here is a scalar multiplication problem, right? We just need to multiply 12 by both of the components of vector u. And so let's do that. This will be equal to 12 times 7i plus 5j. And if you wanted to, you could also use the standard vector notation. I'll show you what that answer looks like in a second. But if we multiply 12 by both of these terms, this will be equal to 84i plus 60j. Or in the other form, that would be 84, 60. All right, either way, that is the vector that results from this operation. The dot product of vector u and vector v gives us a scalar, and so a scalar times a vector is just going to be a scalar multiplication problem, and so we had 12 times vector u, which gave us this vector. All right, let's take a look at our next one here. We have vector v times 2 times vector u, and for this calculation, we can actually use another property of vectors and the dot product, which is that it doesn't matter when you multiply this scalar multiple by vector u and vector v. You can multiply it by vector u and then multiply that by vector v, or we can pull that scalar out and have 2 times vector v times vector u, like that, all right? These two statements are equal. That is another property of the dot product. It does not matter when you multiply that scalar by either of these vectors involved in that dot product operation. All right, and the reason why this is useful is because, once again, we already calculated the dot product of vector v and vector u. We found that it was 12, right? We used that in this calculation as well. At the very beginning of this video, we found that vector v times vector u, the dot product of those vectors, was 12. So this is equal to 2 times 12, which is equal to 24. And so 24 is the result of vector v times 2 times vector u. All right, and so hopefully now you're starting to see some of the benefits of knowing the properties of the dot product, because it made this calculation a whole lot simpler. We didn't have to multiply 2 by all of the components of vector u and then perform the dot product with vector v. We could just simply pull that scalar value out and multiply it by a dot product value that we already found. We already knew that the dot product here was 12. Okay, and we're going to be able to do something very similar for this last calculation. For this last one, we want to find vector v multiplied by vector v plus vector u. And what we can do here is use another property of the dot product, which is that the dot product is distributive. We don't have to add vector v and vector u and then multiply it by vector v. What we can do is multiply vector v by vector v and then add that to multiplying it by vector u. And here's what that looks like. We'll have vector v multiplied by vector v, and then we'll add that to vector v multiplied by vector u, right? We just distributed this vector through this quantity, vector v times vector v, and then that's added to vector v times vector u. All right, and the reason why this is helpful is because now we've already calculated the dot product of vector v with itself and vector v and vector u, right? The first two things that we found in this problem were the dot products of vector v and vector u and vector v with itself. The dot product of vector v with itself was 80, and the dot product of v and u was 12. So this is equal to 80 plus 12. And if you don't believe me, just go back to earlier in this video and you can see that vector v multiplied by itself was 80. So we can just substitute that back into this calculation here, and the same thing for this dot product, which is 12, and that makes this calculation a whole lot simpler. We don't have to add two vectors and then find the dot product of vector v with that brand new vector. We can just use one of the properties of the dot product and make use of some prior work to save us some time. And so 80 plus 12 is equal to 92, And so 92 is the result of this calculation. All right, and you would find the same exact answer if you didn't know the properties of the dot product. If you took the extra time to add these two vectors together and then perform the dot product with this vector, you would still get 92. You get the same answer either way. It's just that with this method, you get to it a whole lot quicker, assuming that you already know these two dot products here. All right, so that's just something that you want to keep in mind going forward. And so with that, that is it for this example with these two vectors in 2D. But now let's look at some examples of using the dot product for vectors in 3D. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the video and take a look at the next example. All right, so next up we have these two vectors, vector x and vector z. Vector x is the position vector of the point 2, -1, 1, and vector z is equal to I minus k. All right, now of course, if we write vector z in the standard vector notation, it would look like this. We would have 1, 0, -1, because the coefficient of I is 1. We don't have a j term, so the coefficient of j must be 0, so that's why our y component is 0. And then for the z component, the coefficient of k is -1. All right, and so using these two three-dimensional vectors that each have an x, y, and z component, let's find the following calculations. First up, we want to find the dot product between vector x and vector z. And so if you want to perform the dot product for vectors in 3D, you need to know the following formula. The dot product of two vectors, vector v and vector u, in 3 dimensions is equal to the product of the x components plus the product of the y components plus the product of the z components. All right, so we multiply the x components, y components, and z components, and add them all together. It's the same exact calculation that we did in 2D, except now we have an extra term which accounts for the z components of our vectors. All right, so let's do that for vector x and vector z here. We'll start by multiplying their x components. So we'll have 2 times 1. So I'll write that down, 2 times 1. Then we'll add that to the product of the y components. So we'll have -1 times 0. So -1 times 0. And then we'll add that to the product of the z components, which are 1 and -1. So we'll have 1 times -1. All right, now if we simplify, 2 times 1 is 2. So we have 2 plus -1 times 0, which is 0. So we have 2 plus 0 plus 1 times -1, which is -1. So we're adding -1, and 2 plus 0 is 2, plus -1 gives us +1. And so +1 is the result of the dot product between vector x and vector z. All right, let's move on. Next up, we have the dot product of vector z with itself. So let's calculate that. We're going to be multiplying the x component by itself, adding that to the y component multiplied by itself, and then adding that to the z component multiplied by itself. So we'll have 1 times 1 plus 0 times 0 plus -1 times -1. And so if we simplify, 1 times 1 is 1. So we have 1 plus 0 times 0, which is 0. So we have 1 plus 0 plus -1 times -1, which is +1. So we have 1 plus 0 plus 1, which is equal to 2. All right, and so 2 is the result of the dot product of vector z with itself. Now, if you remember from our 2D example, we said that one of the properties of the dot product is that the dot product of a vector with itself is equal to the magnitude of that vector squared, right? So for this last one, where we want to find the magnitude of vector z squared, we should be able to say immediately that that's going to be equal to 2, because that's what the dot product of vector z with itself was equal to. The dot product of vector z with itself is the same as taking the magnitude of vector z squared. And just to show you that that's true for a vector in 3D, we'll calculate the magnitude of vector z squared here. We'll take the square root of the sum of the components squared. So we'll have 1 squared plus 0 squared plus -1 squared, and we're squaring that magnitude. right? The magnitude of a vector is equal to the square root of the sum of the components squared. So we're taking that magnitude and squaring it. The square and the square root cancel out, so we're just left with those terms underneath the square root, and 1 squared is 1, 0 squared is 0, and negative 1 squared is 1. So we have 1 plus 0 plus 1, which is 2. And so once again, we have found that that property for the dot product holds true, that a vector multiplied by itself via the dot product is the same as the magnitude of that vector squared. Both of them in this case for vector z were equal to 2. All right, let's take a look at a couple more calculations for vector x and vector z. Next up, we want to calculate vector x multiplied by the dot product of vector x and vector z. Now you could go about this the long way and calculate the dot product of vector x and vector z again, but we already calculated this earlier, right? We found that the dot product of vector x and vector z was equal to 1. So this becomes a whole lot easier. We'll just have vector x times 1. We know that this dot product is equal to 1. And if you don't remember that, feel free to go back in the video. You can see that we calculated this dot product and it was equal to 1. And so to save time, we'll reuse that value and just have that scalar of 1 multiplied by x, which means this is just going to be equal to vector x, right? Any vector multiplied by 1 is just going to be that vector. And we know that vector x is equal to the vector of 2, negative 1, 1, or if you want to use your standard unit vector notation, it would also be equal to 2i minus j plus k, right? Positive 2 will be the coefficient of I, negative 1 will be the coefficient of j, and positive 1 will be the coefficient for k. All right, so both of those answers are correct. They both represent the same vector, which is vector x. That's the result of vector x multiplied by the dot product of vector x and vector z. Now let's move on to our next calculation here. We have 4 times vector z times 5 times vector x. Now once again, you could go ahead and multiply 4 by vector z, and then multiply 5 by vector x, and then find the dot product of those two vectors. But that would be a whole lot of extra work, because if you know the properties of the dot product, then you can simply just pull out this scalar multiple of 5 to the front and have 5 times 4, right? This would be equal to 4 times 5 times vector z multiplied by vector x. We can pull that scalar out to the front because it doesn't matter the order in which you multiply your scalars by your vectors in a dot product calculation. So we pull that out to the front, and now we have 4 times 5, which is 20, multiplied by the dot product of vector z and vector x, which once again, we already know what that is because the dot product is commutative, and we already know that vector x multiplied by vector z is equal to 1, right? We found that earlier in this example, and we used that same result for this first calculation. We said that vector x times vector z was 1. And so this is the same thing as vector z times vector x. It's still going to be equal to 1 because the dot product is commutative. It doesn't matter the order in which you have those vectors for the dot product. You're going to get the same answer either way. So if we simplify here, this will just become 20 times 1, which is equal to 20. 4 times 5 is 20, and the dot product here is just equal to 1. And so 20 is the final answer for this calculation. All right, and so now we're on to our final calculation here. We have vector z multiplied by 2 times vector x minus 3 times vector z. All right, now this one looks a little bit more complicated. It doesn't seem like there's an easy way to calculate this. It seems like we might have to actually go through and multiply 2 by vector x, 3 by vector z, subtract those vectors, and then perform the dot product with vector z, but there is actually a way to do it quicker, to make use of our previous calculations. Remember, the dot product is distributive. We can distribute vector z throughout this quantity. We can multiply it by 2 times x, and then subtract 3 times z times z. All right, so that will look like this. This will be equal to 2 times vector z multiplied by vector x, and then we'll be subtracting 3 times vector z times vector z, right? We just distributed this z through this quantity, so we multiplied it by this term. So we have 2 times z times x, and then we multiplied it by this term, so we have minus 3 times z times z. And the reason why this is helpful is because we already know what the dot product of z and x is. It's 1. We have used that a lot throughout this example. And we also already know the dot product of vector z with itself. We found that at the beginning of this example as well. We found that it was equal to 2. So this becomes a fairly simple calculation. This will just be equal to 2 times 1 minus 3 times 2. Right, and then if we simplify, 2 times 1 is 2, and 3 times 2 is 6, so this is equal to 2 minus 6, which is equal to negative 4. And so negative 4 is the result, or the correct answer, for this calculation. All right, so instead of going through all the extra work of multiplying 2 by vector x, and then subtracting 3 times vector z, and then using that resulting vector to do a dot product with vector z, we can bypass all of that work by using the distributive property and our previous work of the dot product of z and x and z with itself. Okay, but I would encourage you to check to see if that is true. See if you can show that this equals negative 4 by going the long route. It's a good way to practice using your different vector operations. You use scalar multiplication for 2 times x and 3 times z, and then you can subtract those two vectors and then use the dot product for whatever that vector is times vector z. Okay, but with that, this is the last part of this example, and this was the last example for this video. But if you do want to see some more examples related to the dot product, I do have a couple more available on my membership site, so feel free to look into becoming a member if that interests you. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.